Okay, two particles A and B are moving down a slope. A collides with B. Find the speed of B immediately after the collision. Okay, well, the momentum before the collision equals momentum after the collision. Okay, momentum is always conserved, unlike kinetic energy that may not, but momentum is always conserved. Okay, momentum before equals momentum after, before and after the collision. So momentum is mass times velocity, so we've got momentum of A plus momentum of B. So the mass of A is 0.4 kilograms, mass of B is 0.2 kilograms. So momentum before is 0.4 times 3 plus 0.2 times 2. Right, after the collision, the momentum of A will be 0.4 times 2. The new speed is 2, so 0.4 times 2. The momentum of B will be 0.2 times, we'll call it V. Okay, so there you go. Momentum after is 0.4 times 2.5, that's A. The new speed is 2.5. And B, mass times velocity, 0.2 times V. We're going to calculate V. Now, if V ends up as negative, it means it's going in the other direction. But we know, common sense, we know that they're both going to be continuing the same direction. Incidentally, this angle doesn't come into it. It doesn't matter what the slope is, because the momentum after is the instant after, and it has nothing to do with the slope. Okay, so finishing it off, 1.6 equals 1 plus 0.2v. So 0.2v is 1.6 minus 1, which is 0.6, divided by 0.2 is 3. Well, that was quite easy, but part B is not so easy. Okay, I've drawn some diagrams here. Okay, the first bit, show that the speed of B immediately after it hits the barrier is 0.5 meters per second. So just concentrate on this. So we're interested in when B hits the barrier, okay, and it hits the barrier at 0.4 seconds. Hits the barrier 0.4 seconds after the collision. So this is at the collision. So at this point t is 0. Okay. Okay. So immediately after the collision, B, its immediate speed is 3. I haven't put A in. Okay, A is irrelevant to this little calculation. Okay, so B is going to continue on down. It's going to hit the barrier, and we just want to find out what the speed of B is at this point. Okay, they don't coalesce because it says that in the question. It would say that if they did coalesce. So that means A has nothing to do with it. Okay. Now it's a smooth slope. If you look back at the previous page, it's a smooth plane. Okay, so that means there's no friction. So on my force diagrams, I'll put in the weight, 0.2 kilograms, so it's mass times acceleration due to gravity, 0.2 g. I'm not putting any friction in because there isn't any. Now I could put a normal reaction here, but I'm going to be resolving down the plane, and the normal reaction is 90 degrees, so it's got nothing to do with it. And we don't need to work out the normal reaction in terms of friction because there isn't any. So that's the only forces relevant to my calculation. Okay, to work out the speed at the barrier, I just need to do a Suvat equation. You just need to use the Suvat equation. So I need the acceleration. So we can calculate the acceleration from this. Okay, it's quite a simple one. No friction, it's just down to the weight and the slope. So let's resolve down the slope. Right, I'm resolving down the slope. So this 0.2 g has a component down the slope, and it's either going to be 0.2 g cos this angle, or it's going to be 0.g sine 30. So I prefer to use the 30. Okay, so that's going to be 0.2g sine 30, and that's it. That's the only force we've got. Okay, so there's our F. F equals ma. It's not in equilibrium because we're going to acceleration. So there's our F. Our mass is 0.2 kilograms, and A is what we're trying to calculate. Let's put that with a double arrow. That's what we're trying to calculate. Okay, so we've got 2 times 0.5 equals 0.2a, and half of 2 is 1. So A is 1 divided by 0.2. Okay, so A is 1 divided by 0.2, which is 5. So we've worked out the acceleration is 5. It's constant acceleration because this is our only force and this is constant. If you have a constant force, you have a constant acceleration. If you've got a constant acceleration, we can use that. Okay, let's write in what we know then. Okay, S, we don't know the distance, we're not interested in it. U, our initial velocity is 3. Our final velocity, well, that's what we're trying to find out. Call that V. Acceleration is 5, and our time when it's at the barrier is 0.4. So let's use the simple one. V equals U plus AT. V is what we're looking for. U is 3. A is 5. And T is 0.4. That also comes to 5. So V is 5 meters per second. Okay, so it's travelling at 5 meters per second immediately, just before it hits the barrier. Okay, so we're looking for the speed immediately after it hits the barrier. Well, the barrier slows it down, and when it hits the barrier, the speed is reduced by 90%. So nearly all of it's gone. So if you subtract 90% from 100%, you get 10%. So it's going to be 10% of what it was. Okay, so after it hits barrier, the speed is going to be 0.1 times 5, which equals 0.5 meters per second. Okay, at T is 0.4, B has just hit the barrier, and it's travelling upwards up the slope at 0.5 meters per second. Okay, A is still travelling down; it hasn't changed direction. So they're both gonna collide. They're going to collide at T is 0.44 seconds, because that's what it says in the question. Okay, so here's the diagram of them colliding. So we just need to calculate VB, the speed that B is going up the slope, and VA, which is the speed that A is going down the slope at T is 0.44 seconds. Okay, I've put a force. On B, which is exactly the same one. It's the force due to weight. That causes acceleration. It's exactly the same as it was before, so it's going to be exactly the same acceleration. Okay, so the acceleration is again going to be 5, but if we think of positive going up, the acceleration is going to be a negative 5. Okay, because the acceleration is slowing it down. Okay, let's do a SUVAT calculation to work out VB. Okay, positive is up, so that it's initially going up, so it's positive. we're looking for v, well that's really vb, isn't it? The acceleration is acting against, it's slowing it down, so that's negative, and t is 0.04. Okay, so v equals u plus at. Okay, I've done that. vb comes to 0.3 meters per second. Okay, so there you go, b is travelling up at 3 meters per second. So we need to calculate VA. Right, so that calculation for VA. Okay, we're going from here to here. Well, downwards is going to be positive. So we start with initial speed of 2.5 because that's what it says in the question. That's what we're looking for, the final speed. The acceleration is exactly the same. It's 5 meters per second, but the acceleration is going with the in the direction, so it's positive. T is 0.44 because we're going right from the first collision to the second collision, so that's 0.44 seconds later. Okay, let me briefly show you why the acceleration is exactly the same. Okay, so here we go. Resolving down the slope, 0.4 g sine 30 is the force equals mass times acceleration, 0.5 a. So divide by 0.4. Look, you can see the 0.4's cancel out. So a will be 5. So the the mass is irrelevant. Okay, so now I'm doing a VA calculation here using SUVAP, and I got VA as 4.7. So on the second collision, A is travelling towards B at 4.7 and B is travelling towards A at 3. Okay, finally, on the second collision, the momentum before equals the momentum after. The momentum before is mass times velocity of A plus the momentum of B, mass times velocity. It's going in the opposite direction, so I've got a negative velocity here. Okay, so there's the momentum before. Momentum afterwards, they're going to coalesce, so their combined mass is going to be 0.4 plus 0.2, which is 0.6. So they're like one body. So 0.6 times V. Okay, so we're talking positive is down. So if V is positive, then their combined speed will be going down. Okay, if it's negative, it will be going up. Okay. Okay, final calculation. Okay, final calculation, momentum before is 1.82 equals 0.6 v. So divide by 0.6 and the speed is a positive 3.03. Therefore, they're coalescing together and travelling downwards at 3.03 meters per second.